All right, let's talk about processing graphs. I mean, massive graphs. If you've ever dealt with deeply connected data, you know it can get really complex really fast. Today, we're diving into a super powerful model that helps tame that chaos, the Pregel API in Apache Spark's GraphX. Let's get into it. So, first things first, why do we even need a special tool for this? If you're comfortable with traditional databases, you might be surprised to find out that they kind of hit a wall when it comes to graphs. And this is a super common question. You're probably thinking, look, I know my way around SQL. I can write some pretty complex joins. Why is something that sounds as simple as finding friends of friends a total performance nightmare? It seems like it should be easy, but in a relational world, it is anything but.
And that quote right there, it just hits the nail on the head. Relational databases are built to think in tables, rows, and columns. So to follow a path or a trail of connections, you literally have to join a table back onto itself and then do it again and again. Every single one of those self-joins is expensive, and the cost just explodes the deeper you try to go. They just weren't designed for that kind of work.
Okay, so that's the problem, and this is where the solution comes in, the Pregel model. It was originally cooked up at Google, and it gave us a completely fresh way to think about doing computations on huge graphs. It's the inspiration for a lot of modern frameworks, including GraphX. So what is it really? At its core, Pregel is a model for parallel computing. The big idea is to take a huge, complicated graph problem and chop it up into a series of small, manageable iterations. These are called supersteps. And during each superstep, every single node or vertex in the graph gets to do a little bit of work at the exact same time. We're talking potentially billions of nodes all computing in parallel. That's the secret to its incredible scale. And if there's one phrase you should remember, it's this one. The whole philosophy is to think like a vertex. It's a complete shift in perspective. Instead of trying to write some master program that sees and controls the whole graph, you just write a tiny piece of logic from the point of view of a single, humble node. It sounds simple, but this change in perspective is what makes everything else possible. So what does it actually mean to think like a vertex? Well, first off, every vertex in the entire graph is running the exact same simple program. And that program only has local information. The vertex knows its own value, it knows who its immediate neighbors are, and it can see the messages that were sent directly to it. It has absolutely no idea what's happening on the other side of the graph. All it can do is receive messages, update its own state, and then send new messages out to its neighbors. That's it. This limited local view is what lets the whole thing run in parallel without descending into chaos. Okay, so that's the big idea. But how do we actually put this to work? Well, this is where Apache Spark's GraphX library comes in. It takes that powerful Pregel concept and wraps it up in a really clean, functional API that lets you build these iterative algorithms without all the boilerplate. Now, to really get where Pregel fits, it helps to compare it to another function in GraphX called aggregate messages. You can think of aggregate messages as like a Pregel Lite. It's perfect for one-shot, single-step jobs, like, say, counting how many neighbors each node has. But Pregel is for the heavy lifting. It's built for those complex, multi-step algorithms, like finding the shortest path, where information has to ripple through the graph round after round until the answer finally emerges. We've thrown that word supersteps around a bit. Let's really dig into what they are, because they are the synchronized engine that makes this whole thing go. This is how you get billions of computations happening in parallel without everything getting tangled up. A superstep is basically one round of computation for the entire graph. Think of it like there's a global conductor with a baton. When they wave it, every vertex does its little computation in parallel. But, and this is the important part, nobody is allowed to start the next round until every single vertex has finished the current one. It's a hard stop. That global synchronization is what keeps the entire process orderly and predictable. So let's walk through the life of a single superstep. Step 1. Each vertex gathers up all the messages that were sent to it in the last round. Step 2. It runs your program, using those messages to maybe update its own value. Step 3. Based on that new value, it might decide to send out new messages to its neighbors. Now, those messages don't get delivered right away. They're queued up for the next superstep. And finally, step 4, the most critical part, everything pauses at a synchronization barrier. The system waits until every single vertex is done sending its messages. Only then can the next superstep kick off. Now, this brings up a really crucial technical detail. What happens when a vertex gets a bunch of messages at once? They get combined using a merge function. And that function absolutely must be commutative and associative. Why? Because in a big distributed system, you have zero guarantees about the order the messages will arrive in. By making the function order independent, you ensure that you get the exact same predictable result every single time, no matter how the underlying parallel execution happens. It's key for deterministic results.
Okay, let's do a quick recap. The big takeaways here are: 1. Your standard relational database just isn't built for deep graph traversals. 2. Pregel gives us this brilliant think like a vertex model that makes writing iterative algorithms much more intuitive. 3. GraphX gives us a nice clean API to actually use this model. And 4. The whole thing is powered by these synchronized supersteps that make massive parallel processing possible and predictable. So that brings us to the final question, and this one's for you. Now that you understand this model, this idea of nodes passing messages to each other in synchronized rounds, what kind of really complex, iterative problems could you go out and solve with it? Think beyond the textbook examples. Maybe it's modeling how information spreads in a social network, or optimizing a massive supply chain, or even uncovering hidden fraud rings. The potential is huge.
And that's our look at the Pregel API. Hey, if this helped you connect the dots, do me a favor and share this explainer with someone else who might find it useful. And of course, be sure to subscribe for more deep dives. Thanks for tuning in.